dear colleagues, participant editors. We would like to present you the result of our researches. The subject of one is model of graphic object identification in a video surveillance system based on a neural network by Author Andrei Sahun, Vladislav Khaidurov, and Viktor Bobkov. Creation and implementation of object identification system within various technical systems is explained by the demands in a large number of contemporary information systems. Effective and high-quality identification of any objects can be achieved by intelligent systems. The most graphic object identification systems are based on mathematical models. To obtain an object identification system, it is crucial to obtain a artificial intelligence neural network model mathematical. A separate challenge in object identification model based on the neural networks is the classification of recognized objects. Also, we have to create here a function to analyze video frames and utilizes test databases for initial object identification in individual static frames of the video sequence. According to the task conditions, it is rational to base graphic object identification model on the mathematical framework and algorithms of neural network. Here we used deep learning neural network models, which allows to train a model to predict outcomes based on a set of input data. The neural network here includes the input layer of the neural network takes initial input data. In this case, there are 4 neurons in the output layer. Intensity of each pixels for red, green, and blue channel, and have features for each of the considered objects. And the input layer passes this data to the first hidden layer. As the input of our model functionality is the object class. The MATLAB VGG16 function was chosen for graphical object classification. This function represents the architecture of a deep neural network. It includes 16 convolution and fully connected layers. Input layer, convolution layer, fully connected layers, and output layers. Identification of objects based on these machine learning methods occurs through the re-evolution of the weights of connections between neurons. The weight factor determines the importance of the input data elements. There are some specific methods for measuring this distance between features vectors. Here you can see this one, but we have choose Euclid distance because its simplicity and it gets like calculated way to get the path between 2 points for classification. Very important part of our research is training and testing our models. To ensure the operational functionality of the models, the following steps were taken. First of all, loading test datasets from the free Kyiv database sets, preparing a repository for test loading samples. And here we declare individual classes of identified objects like skies, building, poles, and so on. The resolution of training frames is set to 360 to 480 points of the video stream. A neural network model for the identification of graphical objects returns a specific set of numerical values for the identified objects. To obtain central value of an ordered set of graphical frame data, we use a function known in MATLAB as median. Initialization parameters for neural network training and definition of the error functions for our neural network you can see here. It is needed to define the classifier gradient scales to perform cluster analysis and the final classification of identified graphical objects. As a reference data, we will take the informational competence of the color channels of the identifiable image for red, green, blue channels in range from 0 up to 255. Reference information vector for class identification are defined as well. For example, we can see here 11 classes and 31 subclasses. And reference information vector for building and structure identification, for example, for bridge, includes three color components: 000 for red, 128 for green, and 64 for blue pixel color. As color channel reference map for highlighting the classes of indication object contains a RGB color channel vector for 11 basis classes, and the value of this for each class names you can see here. The total number of training images is 421 and the number of test images is 280. As a result of training, the weight of each class can be determined. In this table, we can see class weight which have been calculated for 11 classes and frequency chapters of the occurrence of weight for individual classes on specific frames in this column. And the practical application of the developed identification system we can see in this slide. We observe the identification result on the demonstration test frame of objects subjected to further cluster analysis. The practical application of the developed identification system implies that the identification results were presented not in a visual graphic form, but in the form of numerical data array, allowing this result to be further used in more complex system. Here we can see in this figure we can see original graphical frame for testing the identification model, and in this figure we can see the legend for the identification algorithm classes. A histogram of the frequency of occurrence of identification classes and subclasses of object in the identification zone of video surveillance system we can see here. And as a result, the identification of object from the video data stream of perimeter surveillance cameras demonstrate an average occurrence of 96 across all cameras in the tested plans. Examples consist of 20 videos for the duration in 68 seconds each. Thank you for your attention, and Waiting for your questions.